When you begin a course like this, you have ambitious plans to tell the viewers a lot of things. You keep on doing it and planning more and more and adding things that you actually like yourself, because most what a person can do at the most is to tell in many ways a story of his love. So, he would really talk about what he actually likes in the subject. But suddenly one realizes that these sort of video courses are marked by certain amount of fixed lectures, and then suddenly one realizes one is at the end of the course. Today is the last part 1 lecture. So, it is a good idea that we would do some advanced topics as we were discussing yesterday, and we will talk about the projected subgradient method. I am not going to write down all the details what I had written down yesterday, because it was already done. Now, tomorrow possibly I have to wind up this course with giving you some very major ideas, but lot of things in optimization which I have not been able to speak about here. For example, what happens if the data is corrupted by noise? There is a random variable which has come into the data, chance based input, and on which the designer or whoever especially in the engineering stream has no control on. What he can probably have some idea from the experience, he can have an idea about what sort of noise has come in, what sort of probability distribution such a random variable agrees to. So, the presence of noise or stochasticity is a very fundamental thing in optimization. Such a thing cannot be a part of an elementary course, because one needs to be trained in much more things in order to handle stochasticity in optimization, but for engineering problems stochasticity is a very big requirement. It is a fact that comes in naturally. We have not discussed any stochasticity here. So, the question is that these issues, remember that whenever I have a algorithm, and I have always stressed that you need to show that your algorithm works by showing the convergence analysis, does not mean that that algorithm is superbly efficient, that once you start with the starting point it will rush towards the solution. For example, the steepest descent method that we discussed long back in the course is a very good one, and has very good convergence for the quadratic case, very good convergence for example, very good convergence for the convex cases, but the problem is the following, that it may not rush you towards the solution, it can be very slow. So, there are so these sort of criticism that a convergence analysis does not lead an algorithm to be very good enough for a given problem, and these criticisms are actually valid. But these convergence analysis also brings into light the quality of the algorithm itself, the nature of the behavior of the optima themselves, the nature of the behavior of the iteration sequence. It tells you a lot about the nature of a particular algorithm, which has huge qualitative value. So, for example, I would like to show to you at least through this. So, this is the original paper written by Boris Polyak, called the minimization of unsmooth functional. So, it was published in USSR, and then later on it was translated to English by D. E. Brown, but this paper I I think you can now read the name, minimization of, they did not write non-smooth functionals, but they have written unsmooth functionals. So, that was the English translation, and it talks about, it gives a unified method for both the smooth case and non-smooth case, and where the Polyak step length that we had yesterday discussed had actually been considered. Now, let us suppose we have a sequence generated by the projected subgradient method. The projected subgradient method is, if you want to be more erudite, has to be written like this. Sorry. X k plus 1 is projection on x So, this is the projected subgradient iteration scheme, and that is what we are going to use. Now, but suppose we are given that x k which are in X is generated by the projected subgradient scheme, generated. So, if I call this as the PSS scheme, projected subgradient scheme generated by PSS. So, suppose x k is generated by PSS, and your step length alpha k, suppose now your step length is chosen like this. So, it is a number lying in the open interval. So, at every k your step length will change depending on your choice of g k. Of course, here we are assuming that we somehow have come to know about the infimum value, but we do not know the x star at which the infimum value would be achieved, and the whole process is to find that x star. The whole process is to find that x star using this scheme of iteration. If this happens, then the most fundamental fact about the projected subgradient method, that it does not tell you that the functional value is reducing, only tells you that the k plus 1th iterate is much nearer to the solution x star. So, whatever solution x star you take, so this fact is always true. Sorry, capitalized. So, distance of x k plus 1 from the solution set is always strictly lesser than the distance of x k from the solution set. That is the meaning of this, because now you can take infimum over x star on both sides to come to the conclusion that distance or d of x k plus 1, a distance function, this strictly less than the distance. So, once you take the infimum, the distance of a set C, if I want to remind you, distance of a set from our point y outside a set C is given as the infimum of norm x minus y, where infimum is taken over all x in the set C. So, using that, so that is what happens. So, I will prove this fact to you. So, how do I write this one? So, here is a little bit of art of doing algorithmic analysis. So, this estimate is very important, this actually brings out the character of the projected subgradient method. So, this whole square is xk plus 1 is nothing but the projection A very important fact about projection is its Lipschitz behavior, but we have not spoken anything about Lipschitz functions in detail in this course. So, we would say that if so for any projection mapping, say you take the projection on the set C, then the norm of projection of C. So, you take any y and z in Rn, this is always less than equal to y and z can be in C also. So, I can write this thing as and with x star is in C, the projection of x star on the set C is going to be x star itself. And that is what you have. Sorry, there must be an inequality, but the important fact is not just that there is an inequality of the distance, that given take any x star, this is always maintained, but when you take the infimum you have the inequality here less than equal to times. So, now once you have this fact, then you can apply that result to show that this is nothing but now I have to take the whole square because I have squared both sides. Once I have done this, then I can open the norm by writing this as I will block these two together and have so, this is how you open the norms. Now, once you have opened the norms like this, the next step is the following. Now, observe that Gk is in del f x k. So, Gk is element of del f x k that would imply f of x k minus f of x star, which is f star, sorry, making a mistake. F of x star minus f of x k is g k, x star minus x k. So, what you have is minus so if we take the negative, so what you would have, if you just take it this to this side, you will have g k x k minus x star. Take it to this side, you will have f x star minus f x k, sorry, so you will have f of x k minus f of x star. now we are going to use a subgradient inequality here. So, I will just write down the inequality again. So, x k plus 1 minus x star whole square is now less than x k minus x star whole square. You can take club in the minus here. Once you club in the minus here, it will become plus here and it will become x star minus x k, and that will immediately give you that it is less than f x k minus, it will give you f x star minus f x k. So, you might just not bother about the last this one, it is just the same thing. So, this means I will have minus 2 alpha k f x k minus f x star, which I can write as f star, but okay, just does not matter, plus alpha square norm alpha this, but this one f x k minus f x star is bigger, f x star is smaller. So, this is positive. So, and this is, so this when you, and this is positive. So, this whole thing is negative. So, this is okay. And now alpha k, so this goes off. So, this is less than this plus alpha k square there is no doubt that alpha k is less than this quantity. So, this is, there is no doubt that alpha k is less than the square of this is positive. And now, here what we have to do is, now we have to use the fact that alpha k is less than this quantity. So, you have x k plus 1 minus x star whole square is less than equal to, now you have to take into account this one. So, you write x k minus x star whole square less than, now you have to come up with the alpha. So, maybe you can take negative twice alpha k, which is out. Now, you have f of x k minus f x star minus alpha k norm g k square. I would tell you to finish this calculation by putting in the values of alpha k to show that this is less than norm x k minus x star square. Now, once this is done, we would like to go and, so this is also a motivation for the use of the Polyak step length. So, if an alpha k is chosen of this form, then you are almost, you are sure if it is alpha k is chosen between these two numbers, then this is actually happening. In fact, this is strictly, in fact, this becomes strictly negative. So, because alpha k is not less than or equal to, alpha k is strictly less than this quantity, strictly less this. So, this becomes strictly less. So, if when alpha k is taken to be equal to that, this become less than or equal to. So, it makes sense to use that particular choice of alpha k, and that is from where this Polyak step length is important. Now, we are going to try to prove or give a sketch of the proof of what we intended to show yesterday, or we mentioned yesterday, that if the assumption 1 means if the step lengths, if alpha k is strictly greater than 0, limit of alpha k is equal to 0 as k tends to infinity, summation alpha k, k is equal to 1 to infinity is plus infinity, and summation, all of these has to be satisfied, the step length has to be chosen, k equal to 0 if I want. is k 1 by k plus 1. So, if this happens, if gk is bounded, and now because I have not given you the mathematics of the fact that the subdifferentials are, if you take finite valued functions from Rn to R, the local bound, there is something called local boundedness of the subdifferential, and that would lead to the fact that that norm gk is bounded, right. So, as gk is element of gxk and xk is, no, we cannot say that, sorry, I made a mistake in the last class also, let me admit that mistake. We have not yet proved that xk is going to x star. If xk goes towards x star, then we can say that gk is bounded. So, that is what we really have to prove, that xk is going towards x star. So, gk has to, the norm of gk, this is assumption, is a bounded sequence. Oh, then we are proving that actually unless you have xk going to x star, you cannot use that whatever I am calling as local boundedness property. So, please do not worry about the local boundedness property at all, but remember when Polyak wrote those things, these are essentially done for functions which are extended valued. Of course, the xk's are all in the domain because they are in the feasible set and over which it has to be finite. So, or must the domain's intersection with the feasible set must be non-empty. So, you need not get too much bogged up with it, but we have to take this thing, but if you take the Polyak sequence, you do not have to bother about this boundedness of this norm gk. If this is assumed, then xk goes to x star, and obviously by continuity of the function f, if it is, of course, if you do not have continuity you have to show that, but if you have continuity of the function f, then it is automatic, this goes to this. So, these two things happen, but our case this will happen, will imply that this will imply this. So, you forget about this word local boundedness that I have used in the lecture. So, this is the assumption I am making. So, you might be asking me why I am proving this result and not the result with the Polyak's step length. See, Polyak step length has this issue. So, what is the Polyak step length? There is a fundamental assumption in the Polyak step length is something like this, which so f star, the infimum value, so it becomes adaptive at every step it is changing because of this, and we know that the particular choice of theta has to be done, that we have written yesterday. Now, the problem is the fact that I know f star. In real computations you cannot have f star, you do not know f star, of course, because you are supposed to find f star. So, it is because if you do not know f star, you really, it cannot be an inverse problem that I give you the f star, if I give you the f star then tell you to find the x star, then you use the Polyak step length straight away. But if you do not have such a thing, then what you can do, that you can take an arbitrary estimate of f star and then try to say from x0 go to x1. If fx1 is strictly less than f star, then of course your function value that f star is not a good estimate. So, what you have to come into a situation, so what do you do? So, you reduce the value of f star, you reduce it below fx1, right, and then you again try. So, you try for some times and see that okay, you have got fxk value less than f star. So, you can try it with the, so you take that x1 and then try to the new estimate, you again try from going from x1 to x2 with the new estimate of f star and the step length, means So, from here I start with the point x0 and then I calculate alpha 0 and then I go from x0 to x1 by the standard projection. So, now I check whether if f of x1 is strictly less than my estimate of f star, then possibly this is not a good estimate of f star. F star cannot be strictly less than f x1. So, then I have to choose something which is say f which is strictly less than f x1 and then come from x0 to and then take that x1 as a starting point and then I try to get to fxn, I mean get to fx2. So, what I essentially would require at the end is that okay, I must have my fxn's of this form. It would be enough to have this situation in for my computation for some given epsilon greater than 0. This is the sorry yeah is if f hat is the infimum, then if I do this, then the xn at least should be of this form. So, for some n xn you should immediately have given a fixed epsilon, you can have it in this form. So, f star is f hat is the infimum. No, I made a mistake. F of xn is sorry I made a mistake, it is infimum. So, it should be less than or equal to, rather strictly less than f hat plus epsilon. So, if this happens, then we can take this f hat as this is the definition of epsilon, if definition of infimum. If f tilde is in some sort of an estimate of the infimum, suppose it is the infimum, then for some epsilon greater than 0 I can find an n such that f of xn must be this. So, now if I have an f hat and some epsilon, I can have an xn which is this, and that, and if by luck my fxn value is decreasing, then this f hat would work. So, this is certainly a complicated thing, and so here the Polyak step length is largely a tool which would give me theoretical results, but the problem here again is that these step lengths, and immediately you can find it a step length satisfying this, but the problem again would be this: who would check the boundedness of the norm GKs? How would you know that they are actually lying between something? So, these are questions that come in. So, everything has an advantage, everything has a disadvantage, because you know once you come from to subgradient issues, but this can also be used in the gradient thing. So, but the only advantage in the Polyak case is that you do not have to assume that norm GK is bounded, that is the plus point. Anyway, let us this was a proof given in 1965, and let me just tell you who was the author. This proof was by Shepilov, 5. The proof that we are going to give is by the Russian mathematician Shepilov. Shepilov gave this proof in 1976. So, Polyak's result is in 1969. So, Shepilov improved it in the sense that it is easy to find it, but this is again a drawback. But luckily, if this is happening, some of this also happens. So, for practical purposes, this is the Shepilov's result is pretty interesting in that sense. So, we try to do some proof of this, some outline of the proof. I won't say the full proof, but I will just go and do some outline, give you some idea as to how the proof can be achieved, but that would constitute what would one call as the art of convergence analysis. So, again you start with this fact that you assume that x star is a solution. So, x star, so this goes to, so we have assumed that x star is non-empty. So, we have assumed that x star is not equal to phi. Then let x star is element of x star. Now compute this distance from x star, compute the distance of x k plus 1, square of the distance rather. That is again the same as what we have done earlier. So, this again by that same property written there at that end of the board, this property would lead to the fact that minus minus plus, this minus and this minus plus, and so this is what you have. And then if you write down, open the square, this is exactly equal to so alpha k into, so I am writing this, I am not writing doing too much of stepping, jumping a step. So basically you have 2 alpha k g k inner product x star minus x k, and of course alpha k square plus norm g k square. So we are now combining those two terms and writing it immediately to get if I use this thing repeatedly, what I have is the following. I have that x star minus x k whole square. So I repeat, I start from x k, go to x k minus 1. So here it will be x k, then x k minus 1, so on and so forth. So and then keep on repeating to get the starting point. So obviously it will be up to k minus 1, these things. So repeated application of that one. So S is just a dummy variable instead of that. Not GS, GS is on the top. What you have now, f of x s for any s, guaranteed. Now define C, because you know that this is bounded, this norm g k is bounded, then define supremum of norm g k over k, right, define this. Now say P, I say that the infinite sum, because this is strictly less than infinity, this is P. And this is obviously less than C, and I would have sorry why this happens. I would, this is a very basic question in analysis. So, I would just ask you to figure out this fact. I would not repeat why such a thing happens. This is a very basic question in very basic calculus, basic analysis. So, because we are at advanced level at the end of the course, certain advanced level. So, this is you can figure out why. Now, then going back to what I have here, I can write that x star minus x k whole square is less than or equal to, right, because this part is less than or equal to 0. So, this negative, this is goes, I have this part and this part. So, it will give me sorry, this is x k. This one is this plus. Now, this can be written as strictly less than, because this is strictly less than this. So, there will be a norm J is less than or equal to C. So, product is strictly less than, unless of course, there is a 0 type of thing. In fact, there is no harm if you put it here. So, this will simply show you that from here, homework, show that x k is bounded. So, this is a very important step in any convergence analysis, to show that the sequence that you are generating is bounded, because then you are guaranteed there is a convergence subsequence. So, the idea always is that you show that there is a convergence subsequence which will have a limit point. So, that convergence subsequence has a limit point, and then show actually the whole sequence goes to that limit. So, then the whole sequence is actually going to that limit, and hence and show that the limit is having some properties like that it is the element of the solution set. So, this can be shown as a homework. This is too easy for us to unnecessarily detail on, because you have to understand, because x naught is known, x star minus x naught is actually a fixed quantity, and this is a fixed quantity. Okay. The crucial part of the proof lies here, which we will now analyze. The crucial part of the proof says the following. What Shepilov shows is the following, that in this sequence x k, there exists a sequence, there exists a subsequence x k I such that there, now what we are going to prove, that there exists in x k there is a subsequence x k I, there exists some subsequence or subsequence, right, such that g k I this goes to 0. The proof of this, though it is a very crucial step in the proof of Shepilov's theorem, Shepilov's analysis, this is a very interesting thing in the sense that its proof is not very difficult, because we will use one of the most important tool of the mathematician's toolbox, proof by contradiction. We will say that okay, let us now assume that there is no such subsequence in xk for which this will happen. Okay. Let there exists no subsequence such that subsequence xki maybe. But you know that this result is true. So, though it is less than or equal to 0, it is the subsequence value cannot tend to 0 for whatever be the subsequence. So, given any epsilon greater than 0, so there, or at least they are not given any epsilon, there must exist some epsilon. So, there must be a negative number which will bound this value. So, this value cannot go above that negative number and move towards 0. So, which means there exists epsilon greater than 0 such that gk x star minus x s must be strictly less than minus epsilon. Okay, this is what you have. At least for sufficiently large values of s, this must be true. That is, for some finite number of values, it may go beyond that, but after that, for s large, sufficiently large, it means this has to be the case. Otherwise, it can go to 0. But we are telling that there is no such subsequence for which it goes. So, for s sufficiently large, or these s that you are generating, or the so whatever subsequence you take. So, for sufficiently large index of xs in the sequence, because we are choosing xs from the same sequence xk, this has to be true. Now, if this has to be true, what is the consequence? So, remember, this is a very crucial thing. So, we will just write here that just statement of the result, final result. Sorry, very bad mistake. Now, if this is true, I just want to remind you that sequence x star that xk that I generate need not go to the x star that I have chosen here. So, I will put here as this as some x hat star. The x goes to x hat star, so it goes to some x hat star. So, I have started with some x star in x star because x star is non empty, but that does not mean that the sequence I generate goes to this one. Now, what would be the consequence if this is happening? So, from here the consequence is this is less than minus epsilon. So, why I say that this is a very crucial step? Because now you will see the use of these results. The use of this, we have used this result, but we have not used this fact. Now, because you have this, we have essentially used this and this, but we have not used this result. This is not used. So, this has been used, this has been used, of course, alpha k is anyway greater than 0. This has not been used, this we will not show the use of this, we will just keep it, we will not bother about it at this moment. This has not been used. So, if I use this, if I say that this is less than equal to some minus epsilon, then this as k becomes large, this goes towards infinity. So, this whole thing goes towards minus infinity as k tends to infinity. So, as k tends to infinity, this would imply that x star minus x k goes to minus infinity, which is obviously not true, because I have said that we have already showed that this is a bounded thing. So, I cannot, so this will contradict the fact that this is going. So, what I have said is this fact that there exists no sequence is not true, and there exists a sequence where this takes place. Now, once this is done, when you know this fact, then if you know that there is a subsequence, now you come here, you put x k I here, x k I here, and this x k I and x k I here. So, you take the limit. So, from here what I will now do, I will take this inequality, and in this inequality let me just have a use this fact here. So, I am taking now this inequality. So, I am taking this inequality, and what I am proving? I am proving that this following fact, that f of x k I is greater than f of x star is greater than f of x k I plus g s x star minus x k I. Now, as x k I, sorry, g k I. So, as k I goes to 0, as I goes to infinity. So, as I goes to infinity, which means what? That I goes to infinity, this is going to 0, which means the limit of this, as by using the sandwich theorem, limit of f x k I now. So, which I can call as f star. Now, x k I is a bounded sequence. The bounded sequence of f x k I, there is a convergence subsequence. We assume without loss of generality that x k I goes to some x infinity. So, then I can immediately write by the continuity of the functions f, that limit of x k I tending to infinity is f of x infinity is equal to f star, and x infinity is obviously an element of x star, because this value is equal to f star, the solution, the optimal value. So, x infinity is now in x star, and my job, the problem, the whole proof would end once I can show that x k goes to x star, x k, the whole sequence x k will go to x infinity. So, this is x infinity is my x hat star. So, basically now the proof will end once I prove that x k goes to x star, and this part of the proof I will not prove because we are running out of time, but this is a whole glimpse. What I have done here is to tell you that okay, this is the way things are done. So, there is a crucial point where you start applying this idea, and this idea would be used when you are trying to prove this. You see, so we are using everything, and that is very, very important. So, I have just told you the crucial thing. So, we have shown that we have generated a solution, we have generated a subsequence of x k from which has some behavior, from which goes to some solution, and actually we will show that no, not x star, sorry, I made a mistake, the whole thing actually x k goes to x infinity. Please take care of this. So, that is what we have to prove at the end, which we have not proved, and with this we end our today's lecture, which is the last one basically for the course, and tomorrow we will sum up what we have studied.